Imagine you're trying to build this massive, intricate skyscraper, but there's a catch.
There's always a catch.
Right. The steel beams you're using, they just randomly turn to jelly every few microseconds. Like, if the temperature shifts by a fraction of a degree or if a slight vibration hits the foundation, boom, jelly.
Which sounds terrifying.
Exactly. But that is a reality of quantum computing right now. It promises, unimaginable computational power, but the physical hardware is almost impossibly fragile.
Highly fragile.
So what if you didn't have to invent unbreakable steel? What if you could weave this invisible, hyper-fast nervous system throughout the whole building? A system that monitors the micro-stresses and reinforces the structure in real time.
Long before it ever collapses.
Exactly. Welcome to the Deep Dive. I'm so glad you're joining us today because we are exploring this mind-bending convergence. AI isn't just some future application waiting to run on quantum computers. It's actually becoming the duct tape holding the hardware together and bringing quantum-level chemistry right to our laptops.
It really is.
Yeah.
And, my core belief has always been that knowledge is most valuable when applied. The implications of this are moving way faster than the broader tech industry realizes.
We have some incredibly exciting, highly technical sources for you today. A July 2026 white paper by Cyril Simon, release notes from NVIDIA on their new Ising quantum AI models, and a huge announcement from SandboxAQ about integrating their large quantitative models with Anthropic's Claude.
Yeah, the overarching theme is that AI isn't just software running on a quantum computer. It's the nervous system that makes the hardware function.
Okay, let's unpack this, because you hear about AI and quantum computing separately all the time, but the way they're crashing into each other right now is just wild.
Right. But before we discuss how AI fixes these machines, we really have to establish why they are broken in the first place.
Good point, because this isn't like a standard server having a memory leak.
No, not at all. Standard computing bits are, they're incredibly robust. A 1 is a 1, a 0 is a 0. But qubits, they rely on these delicate quantum states like superposition and entanglement.
Which are notoriously unstable.
Exactly. They suffer from temperature fluctuations, environmental noise, microscopic fabrication variances, and any tiny interference causes the qubit's frequency to drift.
And when it drifts, you get an error.
Instantly. The state is lost.
So the industry's main defense against this has been quantum error correction. And the Simon white paper actually breaks down this massive experiment using Google's Willow processor, right?
Yes, the 101 qubit process.
Right. And they successfully used error correction to make a logical qubit survive 2.4 times longer than a physical qubit. Which sounds great.
It is a critical milestone, but there is a major catch.
There always is.
Error correction only works if the physical error rate stays below a very specific mathematical threshold.
Okay, wait, so it corrects the individual errors, but it can't stop the actual machine from drifting out of calibration over time.
Exactly. What's fascinating here is that crucial distinction between correcting a logical data error and actively preventing the physical machine from drifting into failure.
So, if I'm trying to picture this, it's basically like carrying water in a leaky bucket.
I like that.
Yeah, so error correction is you frantically bailing the water out with a cup, which, keeps you afloat temporarily. But the underlying processor drift means the leak is getting bigger.
Right, the hole is expanding.
And eventually, no matter how fast you bail, the leak gets too big and you sink.
Spot on. And historically, you had to stop the calculation entirely to patch the hole. Manually retune the machine, then restart from scratch.
Which you just can't do if you're running a complex, hours-long algorithm.
Right. So how do we fix the leak while carrying the bucket?
Enter the in-flight quantum mechanics.
Yes. The 2026 Nature paper from Google Quantum AI.
This blew my mind. They used reinforcement learning to adjust the quantum processor while the quantum error correction was running.
Simultaneously. And it improved logical stability against drift by up to 3.5 times on that Willow processor.
Okay, but how? Because they can't stop to take measurements, right?
Right, so they use the exhaust data from the error correction itself, the syndrome measurements.
The clues about where the errors are?
Exactly.
Yeah.
Conventionally, those just tell the system how to correct the logic. But now they serve two purposes. They correct the logic state, and they provide a continuous learning signal for the AI to adjust the physical processor.
Okay, wait, let me push back on this a bit.
Yeah.
So, what does this all mean? We are using the error data to fix the errors. Isn't that like a really dangerous circular dependency?
That sounds like it, yeah.
Like, couldn't the AI guess wrong and just spiral out of control and brick the machine?
If it were a rigid system, maybe. but think of it like adaptive flight control in an airplane.
Okay.
The flight system doesn't assume a constant environment. It reads the turbulence, which are our errors here, and continuously alters its physical behavior to stay stable. For long computations, this is just as important as the error correction itself.
Oh, wow. So it's dynamically fighting the turbulence in real time.
Ex
But okay, real-time adjustments are incredible once the machine is running. But what about actually setting it up? Because getting a quantum computer calibrated in the first place is this grueling, hours-long manual process, right?
It is a massive bottleneck. Manual calibration just doesn't scale.
Which is where vibe calibration comes in. This was a 2026 preprint mentioned in the white paper showing an AI agent that autonomously calibrated 108 qubits in 4.7 hours.
Which is a 4 to 5 times speed up over human experts.
That's insane. And NVIDIA has jumped on this too with their Ising calibration family, specifically Ising Calibration 1.
Yes, the vision language models.
Right, VLMs. So it literally looks at the plots and measurements from quantum experiments to recommend calibration actions. And it's good, like really good.
Highly effective. It scored 3.27% better than Gemini 3.1 Pro and almost 10% better, 9.68% to be exact, than Claude Opus 4.6 on the QKLVL benchmark.
Here's where it gets really interesting, though. Because, I mean, we're talking about hallucinations, right? AI hallucinates. Are we really letting a potentially hallucinating AI directly fire lasers and microwaves at a multi-million-dollar quantum processor?
This raises an important question, definitely. Safety is paramount here.
Because I don't want the AI to just melt the chip.
Right, and it won't because of the safety architecture. The AI operates within an agentic workflow.
Meaning it's not just running wild.
Exactly. It doesn't have unconstrained control. It orchestrates validated deterministic scientific tools. There are automatic rollbacks, strict parameter limits, and anomaly detection.
So it's basically in a straitjacket. It can suggest whatever it wants, but the system won't let it do anything physically dangerous.
Precisely.
Okay, so we've got AI setting up the machine and AI adjusting it on the fly. But there's another massive hurdle, the microsecond bottleneck.
The raw speed of error decoding. This is where classical computing limits crash into quantum physics.
Right, because quantum error correction generates this massive, massive stream of syndrome data.
And if your classical decoder can't process that data fast enough, a backlog builds up.
And the quantum computation just crashes.
Exactly. Google DeepMind showed great progress here with AlphaQubit using a recurrent transformer.
But NVIDIA's 2026 preprint introduces this highly practical hybrid architecture, right? The Ising decoder surface code 1.
Yes, they have fast and accurate versions of it.
And it uses 3D convolutional neural networks, or 3D CNNs, as a sort of pre-decoder.
To handle the local corrections, exactly.
Okay, I have an analogy for this. It's exactly like a hospital triage system.
Oh, I like where this is going.
So the AI pre-decoder is the triage nurse. It instantly handles the obvious common injuries at the front door, which frees up the specialist doctor, the conventional algorithm, to spend time on the complex, uncertain cases.
There's a perfect way to describe it. It passes only the hardest problems up the chain.
And this gets their decoding times down to, what, about 1 microsecond per round?
Roughly, yes.
Yeah.
A pure neural network or a pure algorithm just isn't enough on its own. The future is this hybrid layered approach.
Forming what the white paper calls a cyber-physical system.
Right. You have quantum hardware, classical accelerators,
Yeah.
and AI control all working in unison.
Okay, so we've established that AI is making the hardware stable. But what if you, our listener, want the benefits of quantum-level computation today? Like, without needing a PhD in quantum physics or waiting for a perfectly fault-tolerant machine.
This is where things get really practical for everyday researchers.
SandboxAQ. They just integrated their large quantitative models, or LQMs, with Anthropic's Claude.
Via MCP, the Model Context Protocol.
Right, and these LQMs are completely different from regular language models, aren't they?
Entirely. Standard LLMs are trained on text. LQMs are trained on physics, high-fidelity simulations, and complex quantum chemistry calculations.
So they actually understand the physical laws of nature.
Exactly.
And now, users can use plain English prompts in Claude to run this tool called a QCat adsorption spin.
Which calculates adsorption energy for catalyst discovery.
And catalysts are a huge deal. They underpin like 90% of commercial chemical products, right?
Everything from green hydrogen to complex plastics.
Okay, let's unpack this. I can literally type a conversational prompt into Claude, and it will run quantum-level physics calculations to design a new battery or drug.
That is exactly what is happening. And SandboxAQ is also launching AQ potency soon for screening drug candidates.
And AQ Cell, right, for simulating cellular responses to drugs like checking for liver toxicity before you even make the physical pill.
If we connect this to the bigger picture, this is the ultimate democratization of the $50+ trillion quantitative economy.
50 trillion. Where?
By removing the need to write complex code, they are allowing researchers to leap directly from a scientific hypothesis to an actionable, physics-grounded answer.
That is just incredible. So just to recap the journey for you today, AI isn't just software for quantum computers to run someday. It is the real-time mechanic keeping them stable right now, fighting the drift.
Through NVIDIA's Ising models and Google's reinforcement learning.
Right. And it's the translator making quantum chemistry accessible to anyone through tools like SandboxAQ and Claude.
Navigating the modern tech landscape means watching for these exact convergences. Knowledge isn't just about understanding a single field anymore. It's about seeing how AI becomes the bridge to unlock entirely different scientific domains.
I want to leave you with one final thought to chew on. If AI is already learning to calibrate and stabilize our most fragile, complex physical hardware,
In translating our natural language into quantum physics,
right, at what point does the AI stop being just the control plane and start designing entirely new, unimaginable architectures of quantum computers? I mean, things that human physicists couldn't even conceive of. Something to think about. Thanks for diving in with us.